Okay, we are recording and share desktop. So yeah, desktop, share. Okay, so there we go. So do you all see 2001, like all these exams are available, right? 2001, 2003, 2002, okay. And also there's that screen where I can write on it. Yes, oh, and I should pin me. I'll pin my name. Pin. There we go. All right. My voice is weird today. So without further ado, we should begin. Man, my throat. I haven't been using my voice. I've been typing everything except for the odd lesson. Excuse me. Okay, there we go. Now, folks, what questions would you like done here then? Do we have some exam questions from those 3 exams? Anyone? How were the exams? Dead silence here. I know I've got like 20 of you here, but this is really silent.
They're all right.
Yeah. Okay. Any particular ones you'd like to go over?
Any particular ones, for me at least.
Many? Was that many particular ones or?
No. I said no particular.
No particular ones. Okay. Yeah. Anyone else? If not, I'll pick.
Same with Jennifer.
Yeah. So these exams are okay, huh?
Yeah, for the most part, yeah, I think so. That's
a good sign. I hope that's so for all of you. Yeah. Okay. All right. What caught my eye then? Okay. So I'm going on the assumption that you've actually done all of them right now, like all of you. That's the assumption this is. So I'm not going to give you time to go over these or to do them yourself. All right. So what looks good here? Let's see. Okay. How about like 2002 question 6?
I'm sure.
Hello? Is that good? 2002 question 6. Is that cool?
Yeah.
All right. Now I just picked this one out because it has the mean value theorem. And as we go over more and more exams, I want to pay attention to such things like the mean applications. You're a rebel, sorry. Terry's here. All right. So I want to pay attention to questions that involve the mean value theorem and the intermediate value theorem as well. So yeah, as we continue, I'll try to make sure I go over some of those. So in the meantime, here is question 6. Okay, 2002, question 6. All right. Okay, so there it is. All right, so let me open up ink to go here too. All right, so the key thing to note here is first, all right, so you're given a table of values for this function for f the function f and the function f prime. And the thing is that you're given that it is differentiable. And that implies continuity as well. And it gives the values of the derivative on an interval. And so, and we also, the second derivative has the property that the second derivative is always greater than or greater than 0 on that interval. Excuse me. Okay, so first off, with this question, we are to evaluate that integral. So yeah, so what we'll do then is, let's see, managing multiple software here. So here, this is 6a. So what we are doing then is we are evaluating that integral on 0 to 1.5, and then it is 3 f prime of x plus 4 dx. And so, all right, the thing to keep in mind here is that okay, this is in fact equal to the integral 3 times the integral from 0 to 1.5 of f prime of x dx plus the integral from 0 to 1.5 of 4 dx. So that's just basic integration rules, right? And then from there, here, if you take the integral of the derivative, that is basically the overall change in f from 0 to 1.5. Okay, so thus that's basically, what could we say? Yeah, that's basically then, just going to shrink this a bit. So that is basically then 3 evaluating it. So that is 3 times the function itself, right? Because the integral of the derivative is the function. Basically, that's the fundamental theorem of calculus, plus the integral of 4x, the antiderivative of 4x, all evaluated on 0 to 1.5. Yes. So this is basically a little fundamental theorem of calculus question where, yeah, so you're taking the integral of the derivative and you go back to the original function, the antiderivative. Yes. And then we evaluate that. So that would be then 3 times f of 1.5. That's 1.5. Minus f of 0 plus 4 times 1.5 minus 4 times 0. Yes. So you're basically just evaluating the limits of integration, and that basically comes out to be, if you go back to the table, that is 3 times, and then if you go up here, f of 1.5 is -1. And then minus f of 0. Well, f of 0 is defined to be -7. -7, plus, of course, 4 times 1.5. And I do believe that comes out to be what?
24.
Whoops, 24. Okay. So yeah, just a little problem, just evaluating integrals. Yes. Okay. So now B. (6b), write an expression for the equation of the tangent line. So write an equation for the tangent line tangent at x equals 1, and then use a linear approximation to approximate f of 1.2. Okay, that's interesting. So yeah, so first off, okay, we're doing this at x equals 1 is the tangent line location. And so of course we know that f of 1 from the table of values, when you make x 1, then the function is -4. So that is a point on the line. And then we're also given that f prime of 1 is equal to 5 right there. Okay. By the way, you can all see the mouse circling around, right? You all have that. My cursor is moving smoothly over the internet.
Yep.
Yep, that's cool. Okay. Because yeah. So f prime of 1 would be 5. Yes, reading that off there, 5. So that gets us, in essence, an equation, the point. So y minus -4, so that's the y value, equals the slope, which is 5, and then x minus 1. Or, yeah, y plus 4 is equal to 5x minus 5, or if you will, y is equal to 5x minus 9.
Mhm.
Yeah, okay. So then, yeah. Okay, so then that's the linear approximation. If we use the notation we used in class, that's basically L of x is equal to 5x minus 9, right? That's an approximation for the function f, right? And so if we want the linear approximation of 1.2, then that is equal to, you join Cameron. Welcome, Cameron. Okay, so that would be 5 times 1.2 minus 9, which comes out to be, of course, -3, right?
Mhm.
Yeah. Yeah. Okay. Dylan, welcome. Okay. Yeah, okay. So, yeah, now the question is that an underestimate or an overestimate? Well, what do you think?
Overestimate.
It would be, and why would that be so?
Well,
It's in the under.
the function is increasing and it's also concave up. So
Yeah.
if you looked at it, the slope is increasing.
Yes.
The tangent line would hit the x-axis before that point would.
Yes. Yeah, that's true. It's concave up. So it would be, as you say, it would be the approximation is less than. So it's less than prox. is less than the real value? Because it is concave up. I mean, in essence here, if it's concave up, right, then here is your tangent slope, right? And what we have done, here's the real value right there, and there is our approximated value right there. And because it is concave up, and again, just to make this clear to everyone listening here, some of you might understand this, but I just want to make sure you understand. This curve here is the hypothetical graph of f, yes? And if we go to these values, what you'll notice is that the slope of the tangent goes from 0 to 3 to 5 to 7. So clearly on this interval, it is increasing, yes? The slope is getting bigger, 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 which means it is concave up. And if it is concave up, then you can see that our little tangent approximation, which is the straight line here that approximates the curve, it is beneath the true value of the curve, and so thus this is the approximated value. That's the approx, and then that is the real value, the real one, and you can see that the approximation of 3 is beneath it. Yes. Okay. Is that clear enough?
Yep. What's that in words?
All you need to do is mention approximation, concave up on the
It's
interval.
less than it because it's concave up.
Yes, because it's concave up. That's good enough.
Because you're going
On the-
forward.
Yeah, it's concave up on, what you should actually say is you should say concave up on 1.2 on the interval, right? So that's the justification you need to give, is that it is concave up on the relevant interval, right? That's
Okay.
good. That's good enough. Okay.
Yeah.
Cool. All right. Now, I picked this problem because it is a mean value theorem question. So let's go to that then. Let's go here. So, all right. Find a positive number R having the property that there must exist a value C on that interval from 0 to 0.5. Such that f double prime of C is equal to R, and give a reason for your answer. Okay. So we got to find R in essence. So what we recognize here first, let's get us, I don't want to squeeze this too much, but oops. So I don't want to squeeze this too much here. That'll do. All right. So it's initially a little bit of a word salad. You have to, or a bunch, but if you realize what they're asking, because it doesn't use the word mean, the phrase mean value theorem. So you actually have to remember what the mean value theorem is. So I will bring that to your attention before we do this. So the mean value theorem is this. So the mean value theorem, in essence, says, okay, we have some function. So that's a function there. And we have an interval, let's say A to B. Okay. And there, there exists a value C on the interval A to B, right? So let's say that this is
That must be between the y values.
well, the slope, you see, with the mean value theorem, what you do
Oh, right.
is you
Slope is equal to 9 between them.
have, yes, a secant slope right there. So that's the secant line, right, of the curve. So that's the secant of the curve. And what the mean value theorem says, that there is some value C which is about there, maybe, where the tangent, the slope of the tangent is equal to the slope of the secant. That's actually really poorly done. Let me just do a better job of parallel. So hard to write without a ruler here. And without the friction of a paper. I'm not used to work. This tablet is really hard to draw on because it's there's very little friction. But the slope of that secant line there is equal to this, or the slope of the tangent line right there. So that's the tangent.
Mm-hmm.
And
So the
the
tangent equals slope of the secant. Okay.
slope of the tangent equals the slope of the secant. So that's your C value, okay? So that's your C value. So basically the mean value theorem says this, okay? You find the slope of the secant line, which is, okay, you've got 2 points here, right? This is y equals f of x. That's the curve, y equals f of x. And you're going from the y value, which is f of b, minus f of a. This is just good old rise over run over b minus a. So that is the slope of the secant. So that's the secant slope. And then that secant slope would then be at that point C equal to the slope of the tangent. So that's the slope of the tangent of tangent at C. That's horrible. Tangent at C. Yes. And so what the mean value theorem says is that there exists a C value. Yes, there exists a C value. And the criteria for being able to use the mean value theorem is that this function f here must be continuous and differentiable on the interval. I think it's like open interval and closed interval, like open interval for continuity, or closed interval for continuity, open interval for derivative, if I'm not mistaken. But yeah, I'm just going from memory there. So this test will be open book, of course, by the way. It just occurs to me as well. Maybe even though this is open, if this is open book, you know, you want to watch out for open book things in a sense, because they're often, well, I think they're going to be charitable here, but in my experience, though, on other open book questions I have had, they're almost always harder. But I don't think this AP exam will be like that, because I don't think they're trying to turn the screws on you. I think they're trying to be quite charitable. But nonetheless, when you have a lot of material, you don't want to be fishing for it a lot. And so I've always found that in courses with a wide variety of information that you must know, and you know, it's good to write a formula sheet or a summary sheet maybe of the important information. So I would tend to, because why don't we use this to our advantage here? And I might suggest sort of write a formula sheet, or write a cheat sheet with what you think will be the most important information that you might need on this test, right? Because you don't want to be flipping through textbooks or pages and whatnot. You want it to be fast. I don't know if you read my posting, by the way, on Moodle, or the link to the post on Moodle and the summary of it. But on this question, on this test, there are 2 questions. And one of them, I'm just operating from memory now, but it was, one of them is worth 60% of the mark, and the other is worth 40% of the mark. And one of them, you get a bit more time. The first one, you get a bit more time. So yeah, as for the exact time, probably you just want to go look it up on what I've written. I don't have it in front of me. I could quote a number by memory, but if I'm wrong, that would suck. So, but one of them I remember is more time. And so, you know, maybe having a little quick formula sheet. You know, the cool thing about these formula sheets is that on the tests in my past, in courses that I have taken at university where I was allowed a formula sheet, I would put a lot of information or a lot of effort into my formula sheet, or some effort. And, you know, when I put a lot of effort into it, to be honest, I didn't end up using the sheet all that much. And the reason was that the creation of that sheet was a powerful tool for concentrating the important information in my mind already. And so I might have used it a couple times, 3 times during the test, but because I made the sheet, it brought a lot of things to the forefront and of my mind. And it was a good concentrating effort. Yeah. So I don't know, I mean, you don't have to spend all of your time doing this. To be honest, I would spend a lot of your time doing questions. And at some point, you're going to probably want to transition to the AP Classroom, problems, which are designed to help other students study for this particular test. And I would try those for sure at some point. But right now, you know, we've got a lot of time, right? So it's like more than a month now. So this is probably a good use of our time at this point. This kind of review what we're doing right now, doing old questions. I think this is really cool. Okay, is that cool? So now, all right. So getting back to part C, we have F double prime of C equaling R. Okay, fine. So we have, so this is again 6C. We have F double prime of C equaling R, and you want to find out what R is, yes? Now, what we're actually doing here is we're looking at we're imagining the graph of F prime. God, my writing is horrible. Here, imagine the graph of F prime. Equals Y. You can say Y equals F prime of X, right? And just running out of space here. You can add another page. So we're imagining that graph. And so we can imagine that this is the graph of Y equals F prime of X. No, I don't need to write that. So this curve is the graph of Y equals F prime of X, let's say. And then our values for our interval are 0 and 0.5. So that's our A and our B, right? And so we're saying that there is some C in there such that the slope of the tangent to this F graph is equal to that secant slope. So what we are in, the slope of the tangent is the derivative of F prime, which is F double prime of C. Yes? So that, well, I don't like that. Oh, it did that again. Sorry, glitch. There we go. Okay, back. So again, that slope is F double prime of C. Yes? And then this slope is R. Okay? So the secant is the R. And what you are in essence doing then to find R is equal to the Y value of 1.5 minus the Y value, is it? Oh, 0.5, excuse me. 0.5 minus F prime of 0 over 0.5 minus 0. And what's that equal to again? That's basically 3 minus 0 over 0.5, which is, of course, let me know you're alive here. I'm hearing like radio silence. Hello?
6.
6. Yeah. Okay, there we go.
Yeah, that's right.
Okay, so there you go. Okay, so that's the mean value theorem. And I don't know what they're going to ask, but you know, it's one of those things that really could be on there. I think they haven't formally excluded it, and you know, it could show up at some point. I personally like them. They really cause you to think in a deep way. Okay, now this one's a little bit weird. So ideas on this one. How do you understand this one? You're given this value, you're given this function g, and you're told that the graph of this function passes through all the points given on the table. And then you want to find out, is it possible they're the same function? So what do you think?
Does it obey all
No.
the derivative things? Because if it doesn't, I think not.
Yeah. Go on.
It wouldn't be continuous, right?
Yeah. Yeah, that's the thing, continuity. I mean, all you need to do to show they couldn't be the same function is find one exception, right?
Yeah.
Yeah. So, because the thing is that if you know, this function f is defined by a series, I mean, you're given a series of points, right? And then you're also told that it is continuous, which of course then implies differential. I mean, you're given that it's differentiable, which implies continuity. So if g is not continuous, then which it isn't, then you can immediately say they can't be the same function, right? So I think that's definitely one tack you can take with this one. So we can show continuity. So this is 6D. So we can examine continuity. So of course, continuity in essence would be this. Like if you're continuous, if you're continuous at say a, then the limit as x approaches a of g of x should equal g of a. If you want to be continuity at a, right? So at x equals a, right? And then if you're continuous on an interval, then you're going to be continuous for all the values in that interval. Okay, that looks like a 9. There we go. Okay, so all we need to do is demonstrate that g is not continuous. So at one point. So what's the point? If you look at that function, where is the discontinuity likely to occur? Anyone?
X equals 0.
X equals 0, right? Because otherwise they're both polynomials, right? Like 2x squared minus x minus 7. That's like polynomials are always continuous and differentiable on their individual domains, right? So that would be continuous on its domain, and that's also polynomial. But then we have this piecewise thing. So let's
And if it's
examine.
piecewise, it can't be right.
If it's, I'm sorry, I missed that. If it's piecewise, then it can't be what?
If it's piecewise, then it also can't be continuous and differentiable on the thing.
Well, you can have piecewise functions that are continuous across their transitions if you define them properly. But I don't think this one is such a thing. So what we want to do is we want to just evaluate the limit.
Yeah, but the guarantee is in the derivative as well.
Yeah. So let's examine g first here. So the limit as x approaches 0 from the left side. So this is for x less than 0. We take that branch, right? So that is then equal to 2 times 0 squared minus 0 minus 7. And that is, of course, equal to -7. But then the limit as you approach from the right side, x approaches 0 from the right side of g of x. And that is then equal to, now we're using the piecewise part from the bottom one where x is bigger than 0. So if we're approaching for x is bigger than 0, then we need to do that one. Oh, it is continuous though. My bad. Oh, it is continuous. 0 squared minus plus 0 minus 7. So that's equal to -7. So it is actually continuous. So, okay, that's a blind alley. But what we can do then is we can imagine G prime. Right.
Mr. Sheldon.
Yep.
Could you let Hannah in the Zoom call?
Oh, yeah, sure. Yeah. I bet. Okay, cool. There we go. Welcome, Hannah.
The major question that it runs into is if the derivatives are equal, because it's all well and good
Yes.
for the actual functions to be continuous, but the derivatives usually aren't.
Mm-hmm. So let's examine that then. So G prime of X, well, that will, we can just basically sign it this way. So that would be, 4x minus 1, x less than 0, and then 4x plus 1 if x is bigger than 0. So we can evaluate the continuity of that, and we can say that the limit as x approaches 0 from the left side of G prime of x, and that's going to equal -1. And then the limit as x approaches 0 from the right side of G prime of x, that's going to equal +1. So they're not equal. So G prime x is not continuous. And furthermore, G prime just doesn't exist. G prime of 0 doesn't even exist. Yes. So that means G is not differentiable at x equals 0. Therefore, it's not the same function, can't be the same function. Is that cool? Right. Do you want to move on to another question? Any other requests before I move on? Okay. Okay. Any other questions? Should I move? Whoops. If not, then either that one, I think, or that one. Yeah. Okay. This is similar to what we went over last class, I guess. So let's go to another page. So why don't we say then, unless there are other further requests? Okay. So why don't we say then 2002 question 4. So no calculator for this one. So what we're given here, that's the graph. The graph of the function consists of 2 line segments. And then G is defined by the integral of that. Fine. And we want to find G. Okay. All right. Yeah, sure. Okay. All right. All right then. So sorry, do you want me to close the door then of the construction work? Is it? I can close the door if the noise is too irritating. All right, I'll come back.
You guys hear a noise?
Not really. Yeah.
I don't hear a
I
noise
hear
at
a
all.
noise.
I can't hear
Oh.
anything.
It's really quiet for me, so I don't know. Like
Maybe
I
it's
don't
just
hear
like
any noise.
my headphones. They too good.
Okay. All right. Sorry, I thought this microphone was didn't pick up construction noise very well. Okay. So let's see. So G is this function, you know, the integral on from 0 to x of f of t dt. That in essence means that this is like the derivative of G, you know. Okay. So, all right. So first off, all right. So for A, what we're doing here, if we go G of -1, well, G of -1 is equal to the integral from 0 to -1 of f of t dt. Whoops. Right. And so that, now we notice that we're going backwards here, right? Like, you know, from bigger to smaller. So to make it a little bit more intuitive, we can switch the sign and switch the order of the integrals like that. -1 to 0 of f of t dt. And then we go to this graph here. We go to that graph, and we're going from -1 to 0. And so what you've in essence got there is a little triangle with this is 1 right there. And then that height is 3 right there. So you're basically going, this little triangle is that integral, right? So it's basically 1/2 times the base times the height, which is of course 1.5. And then it is negative. Yeah, change back to cursor. So that was equal to basically -1.5, right? Now G prime of -1. Okay, so G prime of -1. Well, as I say, since we have defined this function that way, G of x is equal to the integral from 0 to x f of t dt. We're basically saying that f is the derivative of G. So thus, in essence, we can say that this is the same thing. And then we can just read it off the graph. I like this question, actually. It's kind of pointing it off. And what's f of -1?
0.
0, good. 0, cool. Okay, because we read it off the graph, right? It's just the y coordinate there. And then, yeah, I actually like, this is actually a good review question, although it's kind of the same thing we did last class, but I like it. So G double prime of -1. Well, that will in fact equal the derivative of like f prime of -1. Yes? And that comes out to be, so what is f prime of -1 then? It's the slope. So what's that slope there?
3?
3, indeed.
Yeah, 3.
Right? Okay. Okay, cool. So yeah, and that's A at least. Now, for what value, values of f is she increasing? Okay. So B. So G is increasing. So where is G increasing?
When f is positive.
Indeed. Where is G increasing on the open interval -2 to 2? Okay, so that basically means that G,
-1 and 1.
G prime of X will be greater than 0, right? Yes, that's what increasing means when the slope of the tangent is positive. But G prime is in fact equal to F, whereas F greater than 0. Yeah? So what you're really asking then is where is F positive? And we have the graph of F right here. So again, where is it positive? Take a look. I want you all to
-1 and 1.
from -1 to 1. So it's positive on -1 to 1.
Mhm.
Okay. So there you go. That is where it is increasing. So for the justification of this, what you would want to do is you would want to, in essence, state that inequality where you would have to say, okay, G prime is increasing on the interval, so G prime is greater than 0 on the interval, which means that F is positive, which means that F is positive on the interval. Okay, so you just got to mention the derivative being greater than 0. Cool. Okay. So, okay, for what values on the open interval is it concave down? Okay, so we need to analyze what concave down means. So again, see where is G of X concave down on -2 to 2. Okay, well, if G is concave down, that means concave down means that G double prime of X is what? Positive or negative?
Negative.
Negative.
Negative. So, okay. So then if G double prime of X is negative, G double prime is negative, then G double prime is the same as what? Is the same as F, what?
F prime.
Prime.
Prime of X less than 0, yes? And then we can look at the graph and say, okay, where is the derivative of F less than 0, right? So again, tell me.
From 0 to 2.
From 0 to 2, from 0 to 2. So F prime is less than 0 on 0 to 2 interval, right? So it is concave down there. Cool. Okay. So yeah, so problems like this are really powerful review, I think. I think we should get to related rates problems. We haven't done those in a while. maybe I'll do that conical tank one. Okay. All right. Sketch the graph. Sketch the graph of G on 0 to 2, and they give you a grid on the test. Okay. So sketch. Sketch y equals G of X on 0 to 2. Okay. All right. So in essence, okay. So what do we know first here? Okay, we've in essence, folks, parts C, D, C and B were hints to this, right? Like G is increasing on -2 to 2, or on -1 to 1. And then G is concave down on 0 to 2. So in essence, we have to do something like this. So this is my okay. Boom, boom. X, Y, and then we go 1, 2, -1, -2. So first off, we are increasing. We are increasing on -1 to 1. So it's increasing there to there. And we are concave down on 0 to 2. So I guess you can do that. Concave down, right? Concave down. We note that the tangent slope there, G of 1 is 0. And then if we go back to the graph here, note G of 1 is equal to 0. Yes, right? So there is our, I just want to write on there. See, we have G of 1, or G prime of 1 equaling 0, excuse me. G prime of 1 being equal to 0, right? Because this is the graph of G prime in essence. This is the graph of G prime right here, right? So there, and so we have another place where it is negative right here. But I mean the G prime of -1 will also equal to 0 here, because this is the graph of G prime. It's the graph of F, but it's actually the graph of G prime. And so that will be another tangent slope here. We note here as well that that G prime on this side, I don't want to write that, but we note that this is a negative value. So because that slope is positive, excuse me, what does that mean about the graph of G? Tell me.
Concave up.
Concave up.
Concave up, right? And if we assume it's continuous and we want to make it concave up, then it would look something like that. So there's a little turnaround, and then it goes up there like that. Okay, and that's good enough.
And those two are little like.
Yeah, that's you don't need to, right? But I mean, but that's where you have the horizontal tangent there and there. I'm just adding that for education, but I think the general shape is enough, right? So basically, what we're probably looking for credit is the concave down on the entire interval, yes, here, and the concave up on this entire interval, and the increasing behavior right here, and the decreasing, and then the decreasing behavior right here. Yes, that's what you're looking for. Note this graph here, it's negative, like F is negative here, So that means that G prime is negative. So that means decreasing. So look, decreasing. And here as well, on -2 to -1 is also, the Y value is negative. And so that means that this graph is decreasing. Yes? Okay. So if you are having trouble with this, I would encourage you to spend a little bit of time fleshing out in your mind whether all of this is crystal clear, right? Like, yeah, you should just try to explain it to yourself. Try to link all these things together. This is a great problem for just linking the big picture together about curve sketching. Okay, so if for any of you this is unclear, then just sort of work on explaining it to yourself and just making sure it's all clear what you do. Like draw a diagram and label things and just write it over and again and make sure it's clear in your mind. Okay, so a lot of this review is in your territory. It's in your court, and I can't do it all for you here. I'm trying to help here with these tutorials, and I'll point the right direction. But in the end, you sort of have to explain these things to yourself and make sure it's clear in your own mind to yourself. Are we cool with that?
Mhm.
Cool. All right. Yeah, I really like being in the classroom better. At least I get a sense of how people are reacting. It's like radio silence right now is disconcerting.
Oh, we're good.
Yeah. Okay. So, whoops. Okay, so, all right. So let's move on. And there. Okay. So what was the other one that caught my eye? I don't have a graphing calculator app right now, so it's kind of hard for me to do these without showing you on the screen. Or how about related rates? Okay. Sure. Okay, so there we go. So how about number 5? So we'll call this 2002 question 5, which is a related rates problem. Okay. All right. So, so a container has the shape of an open right curve. We've done lots of these problems in the past. All right. So water in the container is evaporating and its depth is changing at a constant rate. So that's not too bad. Some of them actually, yeah, we've literally done these in this problem like this in the textbook. The other thing we need to go over are differential equation type ones as well, a little more differential equations. I mean, this is kind of that, but yes, I haven't gone over many slope field questions yet, but we'll do this one for now. Okay. All right, so it has an open right circular curve, the container 10 centimeters in diameter, so that gets you the ratios of the sides. Water in the container is evaporating, so its depth is changing by that. Fine. All right, so in essence, what we have here, so this is 5A. So first off, important information, we're given that dH by dt is a nice constant, -3/10 centimeters per hour. Remember units, by the way, right, folks? Units are everywhere in this test, and they do matter for evaluation. So, okay. So find the volume of water when the height is 5 centimeters. Okay, fine. So the height of the water is, so the height of the water at this instant, the height of the water is 10 right here. Opening is 10. Okay. All right, fine. So find volume. Oh, that's easy. when h is equal to 5 centimeters? Well, this is just a straight cone, vertical cone one. Okay, fine. So what we have here then, the diagram looks like this. I'm getting better at drawing lines, or not. Okay, so that is 10, so that is 5. And then the overall height is 10, right? So the overall there is 10. And then here, we have this to be 5. It's badly not to scale. So that is 5 there. So find the volume of the water. Okay. So you can see that the ratio of this is, that is 5 to 10. So it's in essence like this. It's like 5 over height of 10. And this is h. And this is r. So 5 over 10 is equal to 5 over 10 is equal to r over h is equal to 1 over 2. So what we have here in essence is that the radius, 2 times the radius is equal to the height, or the radius is equal to half of the height, which is then equal to 5 over 2 for r, which is equal to 2.5 centimeters. So now that's 2.5 centimeters. And then the volume, of course, of our cylinder is equal to 1/3 pi r squared h. Yes? So then that is equal to 1 over 3 pi, and then the radius is 5 squared, and then the height is, oh, I got it backwards, didn't I? 2.5 squared times 5. What is that, please, folks? Radio silence. This is disconcerting.
32.725 centimeters
Okay.
cubed.
So 32.725 centimeters cubed. Does anybody have an exact value of that with pi?
Or 125 over 3
125 over
pi.
12 pi.
125 over 12.
That, yeah, no, that.
Pi centimeters cubed. Okay. Seeing as that this is, well, this question was designed to be done without the calculator, I do believe, but you'll have your calculator, so it's fine. Okay. So there, that's easy peasy. B, the rate of change of the volume. Okay, yeah. This is exactly what we did in class, right? Like not even with an AP Calc wrinkle, literally the same. So what we have is that V is equal to 1/3. Sorry, glitch. Okay, fine. So that is 1/3 pi r squared h. And what are we given here? We're given h. H equals 5, right? So we want to get rid of the r. So we know that r is equal to, you can see that r is equal to h over 2. So that means then that we get 4, no. These, oh my God. No more undos. So V is equal to 1/3 pi, and then h over 2 squared times h, which is equal to 1/3 pi h cubed over 4, which is then equal to, of course, pi h cubed over 12, right? Okay. And then, are we right here? Good. Okay. And then, of course, we just go dv by dt is equal to 3 pi h squared over 12 multiplied by dh by dt. Yes, and so that cancels to be pi h squared over 4 dh by dt. And then, next page. So then what we do is we, okay. And what are we asked? Find the rate of change of the volume of the water when h is 5. Okay, so that's easy. To squish it in here. dv by dt when h equals 5 is equal to pi 5 squared over 4 multiplied by dh by dt, which is a nice constant, -3 over 10. And so does anybody have a nice constant value, nice exact value for that one?
-15 pi over 8.
Mm-hmm. Now, what are the units, please?
Centimeters cubed per hour.
Good, per hour, right. Cool. So that's fine. All right, so then what we do is we, okay, show that the rate of change of the volume due to evaporation is directly proportional to the exposed surface area. Ha, that's interesting. Okay, so C. All right, so the exposed surface area. So what we have here then, so there's our little water thing here. So this is H and this is R. So that's the cross section of our cylinder, or of our cone, excuse me. Okay, so there's our R and our H, yes? So that exposed surface area there. Well, obviously the exposed surface area there, that is equal to pi r squared, right? But as well, show that that is proportional to the rate of change of water is proportional to. Well, what we probably want to do is we want to probably, yeah, okay. So what we have here then, we can go back. We have that dv by dt is equal to 1/4 pi r squared, or pi h squared, and then times dh by dt. What's the best way to explain this? So that's the one we derived last time, right? And so what we want to show is that, oh, I see how we do it. Okay, fine. So this is a constant number. And so that comes out to be, if we plug this in, 1/4 pi h squared multiplied by -3/10, which then comes out to be, of course, that is equal to -3, and then over 40 pi h squared. So that is dv by dt, right? So the thing is, what we know is that, as from before, we go back, we know that r is equal to h/2, or h is equal to 2r, right? So what we can in effect do is we can do this, -3/40 pi, and then h squared. So h is 2r squared, right? Plugging that in, changing the variable. And then that is equal to, so -3 pi over 40. And then this would be 4r squared. And then we cancel that and it becomes -3/10. 3 pi by 10 r squared. Yes? So dv by dt. And what we notice here is that that is the surface area. Right? So that is the surface area. Yes? Pi r squared. Right? That is this surface area right here, pi r squared. Right? And then if we go back, okay, what we're doing, you know, proportionality simply means this, right? So it's like dv by dt is equal to, proportional just means this, k times a. That's what we're trying to show here, right? But that is the a right there. And then this is the constant, right? So you can see that the constant of proportionality is then equal to -3/10, if any. Is that clear-ish?
That is clear.
Cool. Okay.
Have a constant proportionality. Doesn't matter what it is.
Yeah, it doesn't. But I mean, proportionality simply means, you know, we use this sort of fish notation, right? Like if you want to, what you're in essence showing is that dv by dt is proportional to a, the area, which is the pi r squared, right? That's what you're trying to show. And this here means that, right? So you can write this circled thing here, or you can write that. They both mean proportional. Just assuming that some of you have forgotten what proportionality means, yeah? Cool?
Well,
All right, yeah, what time is it now? How much? Do we have enough? Do you want to go over another one? Do we have time? Or how long have I been going for here?
It's almost 80 minutes.
Yeah, probably a good time to call it then, I'm guessing. I'm getting tired, I don't know about you. Yeah?
Yeah, I guess so.
Yeah, okay. Yeah, so how are you folks feeling about the material?
Pretty okay.
Yeah, other people?
Pretty good, yeah.
Yeah,
Fine.
Yeah, it's not too bad.
relatively familiar with it. Yeah.
yeah, okay. So you're cool with me putting another, is 3 exams for the week a good number, or do you want more? I mean, I've got a lot of exams I could give you. Do you want more than 3 or 3?
I think 3 is a good number.
Yep, okay,
I think it's a good number as well.
cool. All right then, so yeah, 3 a week, and yeah, you can get to 12, 14, 15 exams. That's a good number to have. Don't forget as well to please check out the AP, the College Board site. There's, if you haven't already. And yeah, there are a lot of specific resources for this year's version of the exam. And you can totally check those out as well. But in any case, I will post another list of exams up. It might be the sequential ones like, 4, 5, 6 or something. I'm not sure. Or I might actually go through and pick some ones that I know to have some really great exemplar problems. But yeah, in any case, I'll put those up there sooner than later and with the solutions. And that can be like a bare minimum for you to do. And I hope you're all doing it. I haven't checked the hand-in rate here, but it really is important right now to do some work on this. Okay, I know maybe for some of you, this is going to seem a little bit stressful because you haven't really begun your review process fully yet, I think. I know some of you are doing okay in this, but I'm just talking to maybe some other people that are having, finding this a little intimidating. And just go by the experience of past students that I have had. It always gets better. Like they say, it's students I've had before, we've gone this process, it just gets better and better and better. And as the more you do here. So the point is to increase the number of questions that you're exposed to, and they become more and more familiar. And then we'll start zeroing in on this exam this year, right? So, which has a date that's later than the one we had, right? Well, I don't have the date in front of me. What did I write for the date again? Hello?
I think the 12th.
Yeah, it's like, it's 11 or something, right?
I thought it was 11.
Yeah,
I think
okay.
11:30.
Yeah, we'll make sure we get that right date, right? Please make sure. Okay, just check that date and look at it, right? I know that table is a bit of a beast to read, right? It's got all the time zones in the column headers, and yeah, but all the exams and the row headers. But yeah, so just don't give up. Keep on going along. You'll be fine. And is 2 a week enough for now? Tutorials?
I think so, yeah.
Okay.
Yeah, I think 2 is good.
Okay, that's cool. All right. So yeah, thank you very much for coming. I will post the video to this on an unlisted YouTube link. And yeah, and anyway, take care. And, get exercise. As I say, try to get exercise. It really helps, trust me. Yeah, just do something. It does wonders for the mind and the mood and everything. So try some exercise, like even if it's just like, even around the house, planks and air squats and, yeah. Anyway, so take care and be healthy, okay? And I guess I'll see you Friday though, right? Or is Friday okay? Do you want one on Friday?
Sure.
Sure.
I'm okay with that.
Okay, so we'll do one on Friday then. I'll schedule that in. So we'll keep the Wednesday and Friday open, Wednesday and Friday. And when we need more, then we'll put in the Mondays. I have to warn you right now though, I don't know the landscape as to what other teachers are going to do. And so right now I've decided on a schedule, but I can only put 2 and 2 together knowing that other teachers will want to have some sessions for you as well. And in that regard, I will have to navigate around that. But for now, I'm going to aspire to Wednesdays and Fridays afternoons. Okay. So take care of yourselves, and yeah, I'll see you Friday. All right.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you.
Thank you for coming.
Thanks, Mr. Sheldon.
You're welcome. Take care, eh? Okay.
Bye.
Bye-bye.
Bye.
Okay, bye-bye.
Bye-bye. Take care.